Hello, my name is Marcus Brubaker, and on behalf of myself and the other organizers of this tutorial, Ulrich and Karsten, I'd like to welcome you to the ECCV2020 tutorial on normalizing flows in invertible neural networks in computer vision. This tutorial is aiming to provide you with an introduction to normalizing flows in invertible neural networks generally, as well as to showcase some interesting new examples of applications of normalizing flows in invertible neural networks in computer vision. The tutorial has been broken up into a longer introductory section, which this is the beginning of, as well as a number of shorter sessions focused on specific applications or more advanced topics. I would encourage everyone to watch the videos and come to the live tutorial slots. Schedule is available on the ECCV2020 website to ask us questions and to get more information about any of these topics. Okay, with that, let's go ahead and begin with the first session, which is Introduction to Normalizing Flows. So what are normalizing flows? Normalizing flows are a particular form of probabilistic generative model. Right? And a probabilistic generative model is simply a probability distribution over a random variable, which we'll just call here x, which we're going to attempt to learn from a set of observed data. Okay? And this is going to have some probability density and maybe some set of parameters theta. Okay. Now, why do we care about PGMs? Many of you may already have an answer to this, but just to set the stage a bit, we may want to, for instance, draw new samples from a generative model that we learn. So in other words, this is the canonical example of train a GAN on a bunch of images and then synthesized new faces of people. We may also want to, for instance, use generative models to construct priors or likelihoods that could be used elsewhere. So for instance, we can use it for denoising, or we could use it for image reconstruction tasks and lots of other things. Now, PGMs are actually a very old idea in a sense. There's many different choices that you can make in a PGM. Different choices of distributions, different learning objectives, and different learning approaches all lead to different probabilistic graphical models, right? And many of which are familiar in terms of GANs and VAEs, but this lecture and this tutorial is focusing on normalizing flows in particular. But I'm going to talk just very briefly about some other types of probabilistic graphical models to set the stage for why normalizing flows are interesting. So the first one is mixture models. And in some sense, this could really just be classical statistical methods, okay? But a mixture model is a probabilistic generative model, right? It is a PGM, and it's been very extensively studied for many years, both in machine learning and statistics and elsewhere. It's typically trained using either maximum likelihood or a variational bound on the likelihood, which is the case, for instance, in the EM algorithm. And for a Gaussian mixture model, things like sampling from that distribution as well as evaluating the density is generally straightforward. The downside, of course, as anyone who has a lot of experience working with mixture models, is that it typically scales quite poorly with dimensionality and with added expressiveness, right? In other words, adding one more component to a mixture model, that's really the primary mechanism for adding capacity or adding expressiveness to a mixture model. And especially with more complex, higher dimensional distributions, adding another component doesn't necessarily lead to the improvements in performance that we would like. Another class of probabilistic graphical models is energy-based models. Those of you who've been around in computer vision long enough will be familiar with these. They're fairly powerful, and they've actually had some pretty significant successes in computer vision. Markov random fields and conditional random fields are kind of examples of these energy-based models. Training and sampling with energy-based models can be quite complex, typically requiring Markov chain Monte Carlo even on inner loops. And evaluating the density is possible, but typically only an unnormalized version of the density is easily accessible. So these are kind of classical approaches, but of course, you wouldn't be here in this if we weren't talking about something a bit more recent than this. We wouldn't be running this tutorial. And everyone has probably seen at this stage GANs, at least I would certainly hope so. Okay, the results from GANs are inarguably impressive, right? All of the methods that we've seen before have generally not been successful at capturing the diversity and structure of natural images particularly well. GANs have really stepped up and done that in a big way. They're trained quite differently. They're trained through an adversarial process, which we can actually understand in the context of a probabilistic generative model as minimizing a divergence or a particular integral probability metric, which is different than necessarily just maximizing the likelihood of the data. Sampling from GANs is actually very straightforward. In fact, they are constructed to make sampling easy and efficient. However, evaluating the density is generally not possible. So using them as likelihoods, using them as priors is generally not possible with GANs. As many people know, those familiar with the literature, this is also one of the challenges of actually evaluating progress in GANs, which led to the development of many other kind of qualitative metrics of image quality that have been used since to evaluate GANs. Introduced at around the same time are variational autoencoders. These are a probabilistic form of a latent variable model where we assume that we have some low-dimensional representation that generates our high-dimensional object, in this case an image. VAEs have been quite successful, in fact, in learning these low-dimensional representations, and especially when we want these representations, when getting these representations themselves is the goal of learning a probabilistic generative model. Training is typically done in terms of the marginal likelihood, in other words, with a form of maximum likelihood, but the marginal likelihood is not actually directly tractable in the case of a VAE because we don't know the actual values of these latent variables. And as a consequence, training is done by a bound, the so-called evidence lower bound, or ELBO, or one of the many, many variations on ELBO. Sampling from a VAE, much like with a GAN, is actually quite straightforward. You draw a sample from the latent space, and then you draw a conditional distribution sample of your output given that sample of the latent space. And approximate evaluation of the density function is possible, but it is only approximate, and it's not always clear how good of an approximation that is. Okay, so this is kind of the setup. VAEs, the quality of generated images, have typically not been as good as they have been for GANs. But these are kind of the standard probabilistic generative models that most people in computer vision will have heard of and probably have some experience with, potentially, if they have experience with modern PGMs at all. So this is where normalizing flows come in. Okay, so normalizing flows, what are they at their core? They are a probabilistic generative model built on invertible transformations. Okay, at a high level, they have kind of the following goals and generally following properties. So it is typically efficient to sample from normalizing flows. It is also typically efficient and possible to evaluate the density exactly or almost exactly. We'll talk about that a little bit later. They are highly expressive, and in fact, they are what I refer to as flexibly expressive, which is to say that in a Gaussian mixture model, we will typically adding capacity, for instance, basically just means adding another mixture component. And that's not a particularly expressive form of capacity because it can really only represent multimodality, and you have to really add lots and lots of components if you want to, for instance, represent a distribution that's very simple and maybe even unimodal, but has some non-trivial curvature to it. Okay, normalizing flows are closer to GANs and VAEs in that regard, in that you simply add some more channels or you add some more layers to your network and you get a more expressive model. Okay, they also come with a fairly useful latent representation. This is perhaps a little bit in contrast to GANs, where the latent representation is not as immediately useful because there is no immediate given mapping from image to latent representation. And finally, normalizing flows are actually very straightforward to train. GANs and VAEs, GANs in particular, but VAEs as well, have some pretty well-known training pathologies that make them quite difficult to work with. The fact that normalizing flows are invertible, the fact that you are working on maximum likelihood training, typically makes that training makes the training procedure much simpler. It is just a simple gradient-based optimization for which we can apply SGD, and at least empirical and practical experience to date suggests that it's much convergence and stability is much better than it is with the other issues. And the question, of course, is, okay, great, we could construct lots of generative models that look like this. What are the results? Well, there are lots of exciting new results with normalizing flows coming out every day, but I always like to go back to this result. This is GLOW. This was a paper at NeurIPS in 2018, and this is the one that I think really brought everybody's attention to normalizing flows, because it really showed that normalizing flows have the ability to generate high quality, high resolution imagery while still being able to exactly represent a density function and exactly compute a corresponding density function. And they also, normalizing flows also have the ability to have potentially meaningful and useful latent spaces. This is an experiment from the GLOW paper that I liked, where you're able to morph back and forth between different faces just by interpolating in the latent space. And note that because of the structure of normalizing flows, you're able to actually take any image you want and get the exact corresponding latent representation, and then use that to interpolate, in this case, between faces of one of the authors of the GLOW paper and various notable people such as Geoff Hinton and Neil deGrasse Tyson. Okay, so that's the high level result. Hopefully that's enough to get you excited and get you interested in normalizing flows and want to stick around for the rest of the tutorial and see all the cool applications that we'll talk about. But now I want to dive in and just really tell you formally, technically, what are normalizing flows. So I always like to say normalizing flows are basically just a glorified application of the change of variables formula. So in almost any and every probability course that you take, or at least an introductory probability course, you will come across a formula that looks something like this, okay? And the change of variables formula describes what happens and what's the relationship between the density function of some random variable x, okay, under some transformation f. Okay, so here we have a random variable x, which is some given random variable. We're going to apply a transformation f to that random variable, which is going to give us a new random variable z, okay? And so what is the relationship between the density functions of x and z? Well, this is it. So we have our invertible, this transformation here, f. It has to be invertible for this to apply. We'll talk about that a bit more later. But we have the density of x, and then we have the density of z of the transformation of x. And then we have this last term here, which is a volume correction term. And this basically is a very important kind of piece of this transformation, because it ensures that both z and x integrate to 1 and are valid probability measures in that sense. And it corrects for how much a transformation kind of stretches or compresses a particular space. Okay, we can visualize what this means a little bit. So imagine we have this nice little bimodal distribution here, p of x. And we can map it through some transformation. So the cube root of x here is the one I'm going to use in this particular case. Cube root is invertible, it's differentiable. And so this applies. And so as a consequence, we can use the change of variables formula to figure out what z is. And in this case, it turns out that z, this bimodal distribution run through a function's cube root of x, actually turns into a unimodal or nice Gaussian distribution. Okay. So what does this have to do with normalizing flows? Well, here we go. What we're going to do is we're going to say, let's assume we have some given p of x. This is data. X is going to be our data. This is going to be images. Okay. And we're going to choose some arbitrary distribution over z, which is one that we want to choose to be relatively convenient and easy to work with. P of z here. And now normalizing flows basically says, given this formula, what we want to do is we want to find the function that transforms this very complex distribution over x into a nice simple distribution over z, right? We want to make the distribution of images look like Gaussian noise, okay? And we can do that through this function f, right? And that's exactly what normalizing flows set out to do. Is learn this function f, which transforms data distribution into a Gaussian or normal distribution z which is what gives us this idea of normalizing flows, right? So f here is this function which kind of flows. We'll talk about that in a minute, but basically flows our data distribution into a normal or Gaussian distribution and hence normalizes it, okay? There's two main pieces to these normalizing flows. A base measure, this is the distribution over z that we've picked. Again, typically we pick this to be just a Gaussian with mean 0 and identity covariance. You can make other choices. We won't talk about that much today, but it's certainly possible. And this flow function f, which is what we're going to try to learn. Now, of course, the thing with this flow function f is that it does have to be invertible and differentiable for that change of variables formula to actually apply. And we'll get back to that very soon. Okay. So if that's what we've done, so imagine we have our data distribution x, we have our base distribution z, and let's imagine somehow that we've learned this invertible differentiable function f. What do we do next, right? Well, this is a PGN. Let's ask the question, how do we do density evaluation? Well, that's actually dead simple, okay? Because we have this expression from the change of variables formula, which says the density of x is equal to the density of z times this volume correction term, all right? And so you can think about it like this. What we're gonna do is we're gonna take our images x here, we're gonna run them through some function f, and we're gonna get a sample that's gonna be, which should be drawn from a Gaussian distribution if we've learned f properly. And now we can simply evaluate the density of that Gaussian sample, as well as evaluate this log determinant term, right? This volume correction term, okay? And sampling is actually also gonna be pretty straightforward because it's simply going to be going the other direction. We draw a random sample from our Gaussian distribution, okay? And now what we're going to do is we're going to apply the inverse transformation of f, right? And that's going to take us from this Gaussian distribution back into the distribution of images, okay? So if we have done our jobs properly, if we have learned this function f, and it is indeed invertible, now we have a probabilistic generative model for which we can do exact density evaluation, and we can also do exact sampling basically by construction, okay? Training with normalizing flows is most commonly done with maximum likelihood. And because of the fact that we can compute the density exactly, we can actually write out the maximum likelihood, write out the log likelihood of a set of data points, xi here, in terms of these individual pieces. And so basically, this is our function. Note that pz here, that's just a Gaussian density. F is that function that we learn, in this case parameterized by some values theta. And then we have this log determinant term, which gets added on at the end here, okay? And so now we can just optimize this directly with stochastic gradient descent like we would in any other kind of deep learning application context. But what have I not told you? Well, I've not actually told you anything about these flows or what they are. I've said there's some parametric function, okay? And I said we're gonna learn it so that it transforms images into a Gaussian distribution. But I haven't really told you too much else, right? So I've given you some requirements for it. One requirement, which comes from change of variables, is that it's invertible, right? That means that we can do both density evaluation as well as generation. And it also has to be differentiable. That just comes straight out of the requirements for the change of variable formula. But one of the other pieces that we're going to need to make it practically useful is that it has to be efficient to compute that inverse and Jacobian, okay? Or more precisely, the determinant of the Jacobian, all right? It's not sufficient for kind of the most general cases for the inverse to exist theoretically if we want to be able to do both sampling and density evaluation. Now, there actually are some applications of normalizing flows, which I won't really talk about today, where it turns out that we don't need that invertibility necessarily. And we just need to know that it theoretically is possible to invert f, but we don't need to actually be able to compute it efficiently. But we won't go into that today. Okay. These flows are also sometimes called flow layers or bijections. My mathematician friends will get a little bit testy whenever I call them bijections and whenever people write bijections in papers, because note that bijection really only covers the fact that f has to be invertible. F also has to be differentiable, and if you wanted to be particularly formal, you could call them diffeomorphisms. But for now, I'm just going to stick with kind of the simpler terminology of flow, in order to capture these requirements, okay? And indeed, designing and constructing these flows is the core research problem for normalizing flows, okay? So how do we construct a flow function that is sufficiently expressive and complex that it can transform a sample of images into Gaussian samples? So the first thing that we need to point out is that we're not going to do it in one monolithic flow, or at least we don't have to. If we could, that'd be fantastic, okay? And we're actually going to rely on the fact that we can compose flows together, right? In other words, invertible differentiable functions are closed under composition. That means I can take a whole sequence of invertible differentiable functions, fk, fk minus 1, etc., up to f1, and I can compose them together. And the resulting function f is now itself also going to be invertible and differentiable, assuming all of those f1 up to fk are themselves invertible and differentiable. Okay? That shouldn't really be hugely surprising. Okay, this is just a basic result of calculus. But what this does do is it allows us to build up complex flows from the composition of simpler flows, right? So you can think of this in a deep learning world as stacking layers upon layers upon layers in order to get more and more complex functions, more and more complex classifiers and transformations, okay? And so graphically, we can kind of think of that like so. We start off on the left here with some complex multimodal distribution. We apply F1 to it. We get a slightly less complex distribution. We've transformed it a little bit. We get F2, we transform a bit more, F3, F4, and now we've gradually changed this complex, jaggy looking distribution into a unimodal, nice, well-behaved Gaussian distribution. And we can compose all of these things together, and now we have our one big f of x that transforms our complex distribution into something nice and simple. It's closed under composition, which means that we should also easily be able to get the inverse, and the inverse is also pretty straightforward to understand. So if we have f4 and f4 is invertible, then if we apply the inverse of f4 onto our Gaussian distribution, we're going to get something a little more complex, and now we can apply the inverse of f3 and of f2 and of f1, and we stick all these things together, and what we see is that the inverse of this composition of transformations is just the composition of the individual inverses in a reversed order. Okay, so that means now if all of these functions f1 to fk are themselves also invertible, then the whole thing should be invertible, and if all of them are kind of computationally efficient to invert, then the sequence of them should also be computationally efficient to invert. Okay. The last piece though that we required is the determinant in order to be able to compute that volume correction term, the determinant of the Jacobian to be precise. It turns out that a simple application of chain rule gives us that the determinant of the Jacobian of the entire transformation is just a product of the determinants of each of the individual Jacobians, okay? And so this tells us that if we have an expression or a way to compute the determinant of the Jacobian of each one of those individual flows in an efficient manner, then we can do that for the entire transformation in an efficient manner simply by multiplying them all together. And this particular structure for the determinant gives us a nice little added structure in the log likelihood that we might use for training. And so now we have this extra sum over the individual layers, right? And if you want to think about this in terms of training dynamics for a moment, one of the things that this does is it says that there is every layer basically in some sense has some amount of gradient flow from the training directive, from the training objective, because each one of these log determinant terms is kind of an independent separate term in this sum. Okay. But of course, I still haven't actually given you a concrete invertible differentiable transformation. Now, we can start off with a linear transformation. A linear transformation itself is, or certainly can be, a flow, so long as the matrix itself is invertible. So here's your linear transformation, some matrix A times X plus B. Its inverse is given like this, and that inverse exists, and we can compute it so long as A itself is invertible. And analytically, it's easy to show that the determinant of this transformation, while the Jacobian is just the matrix A, and therefore the determinant of the Jacobian is just the determinant of the matrix A. All right, so this gives us a linear building block for our transformations. But of course, there's some problems with this. So the first really obvious one, which we'll come back to in a minute, but it's that linear functions are closed under composition. So if I can only compose together linear functions, I can never build up anything more complex than another linear function. And we know that we need something more sophisticated than a linear transformation. For instance, basically the only thing that you can change about a distribution is its mean and variance. If you are applying, that you can meaningfully change is the mean and variance if you are only applying linear transformations. Okay. The other problem, of course, though, is computational expense. That inverse, right, is going to be order d cubed for general matrix A in order to compute the inverse or compute the determinant. All right. Now, if d is small, then that's not a big deal. But of course, if we're talking about images, if we want to use this as a probabilistic generative model over images, then if we have 1,000,000 pixels, we do not want to do an order d cubed operation, right? And of course, one of the ways around this is that we can reduce the determinant, reduce the cost of the determinant in the inverses by restricting the form of that matrix. So for instance, for diagonal matrix, we get a linear cost. For triangular matrix, it's quadratic for the inverse and linear for the determinant. Block diagonal matrices depends on the size of the block. And basically, there's many different kind of structures that we can apply and restrict the form of these matrices in order to get more efficient or get determinants and inverses that are kind of more computationally efficient to compute. But that still doesn't solve our problem that linear transformations are closed under composition. So how do we move beyond just linear transformations? In order to do that, we're going to introduce the idea of a coupling flow. Okay, so this is a very general approach to construct nonlinear invertible transformations for whom the Jacobian or the determinant of the Jacobian is computationally efficient to compute. And to do it, we're going to begin in a bit of a strange way, which is that we're going to partition the parameters, partition the inputs rather, into two disjoint subsets, XA and XB. All right. And what we're going to do is we're not going to touch XA, and we're only going to apply an invertible differential transformation on XB. That transformation where this F hat here is going to be another flow. But the parameters of that flow only depend on XA itself. They don't depend on XB. All right. This might seem like a bit of a strange thing to do, but let me walk you through this a little bit more graphically. Okay. So we start off with our input X here, and we're going to split it in half. Okay. We're just going to take the first half and put it over here, and the second half put it down here. Okay. Now this first half, we're going to do two things with it. The first thing we're going to do is we're just going to stick it over here. Okay, so this version we're not going to touch. And we're also going to, at the same time, run it through what we're going to call a coupling network, which is going to be this theta, this function theta that will take in our XA and spit out a set of parameters. And those parameters will then get fed into our coupling transform F hat that will then manipulate XB in order to produce some changed output. Now, and finally, we're going to take this changed output of XB, this transformation, the result of this coupling transformation, and we're going to combine it together with the XA that we have at the top and just concatenate things together. And this gives us the coupling, the forward transformation of a coupling flow. Okay? The inverse of this is actually going to be relatively straightforward, okay? Because all we need to do is effectively take exactly this process and reverse all of the arrows, all right? And we can do that, so we start off with our Z, we split it into two halves, ZA and ZB, we put ZA off to the side on its own, and then we're going to take ZA, run it through the coupling network. Now remember, ZA is equal to XA, so running ZA or XA through the coupling network, theta is going to give us exactly the same set of parameters, which we then plug into the inverse coupling transform. And therefore, because this is invertible, and we've given it exactly the same parameters as input, the inverse of ZB is going to give us back our original XB, and we concatenate these two things together, and now we have the exact inverse of our coupling transformation, all contingent on this F hat. Okay. Now this might seem like I've just pushed the problem off because I still need this inverse coupling transform F hat to, this coupling transform F hat to be something interesting. But the key is that transform doesn't necessarily have to be anything that interesting. It could in fact just be a diagonal linear transformation. Okay. We'll come back to what those coupling transforms are in just a minute. But let's talk, this coupling construction may seem a little strange, but let's dig into why it is. And it all actually comes back to the structure of the Jacobian. So the Jacobian of this matrix, so the Jacobian of this transformation of these coupling layers has a specific structure. And this is what it is, okay? So the first row, that's the derivative of the output ZA with respect to XA. And so in other words, that's just the identity in that first block, that top left block, because ZA is exactly equal to XA, and 0 otherwise because we're just not changing it, and therefore it doesn't depend on XB. Now, the bottom row, if we go to the right, what we see is the Jacobian of that coupling transformation, right? So the derivative of that coupling transformation with respect to XB. Note that it doesn't, that's not the derivative, the derivative doesn't involve theta, and therefore doesn't involve XA, but we do have this other block in the bottom left, which does depend on XA, okay? But the beautiful thing is we don't actually care about the Jacobian itself, okay? In the sense that for normalizing flow, what do we need? We need the invertibility, we've already shown that, but we also need the determinant of the Jacobian, not the Jacobian itself. And so the determinant of this matrix, this is a block triangular matrix, which means that the determinant is simply the product of the determinant of the blocks themselves. And in this case, because that top left block is the identity, therefore the determinant of this whole thing is just the determinant of that coupling transformation, okay? And in fact, this theta can be arbitrarily complex. It can be anything that we want, a multi-layer perceptron, a CNN, whatever you want, because so long as we can compute it, we don't need to invert it, we don't need its Jacobian, we'll need its gradients in order to do learning, but otherwise we don't need anything else special from it, okay? But for this to work though, it's important that we change the splits, okay? Because if we always split XA that we don't, the first half of the vector that we don't manipulate and the second half of the vector that we apply these coupling transforms on, then of course we'll never learn anything interesting about half of our space, okay? And so there's a question of how do we want to change those splits? There's lots of options. You can randomize it. You can alternate splitting XA and XB. And all of this can kind of be captured in the following, which is we apply either some permutation or more generally, we apply a linear transformation to X before we apply the coupling transformation, okay? So we do this permutation or linear transformation. We've already gone over what those linear transformations look like, and in fact, if you recall from linear algebra, the inverse of a permutation is just its transpose, and the determinant of a permutation is either 1 or -1, and therefore its absolute value is always 1. So that's a nice flow that we already have. You can have more complex versions of this. So for instance, the GLOW architecture that I mentioned earlier uses 1-by-1 convolutions, which is basically a block diagonal linear transformation with repeated blocks and so forth, right? And so now we take this permutation of this linear transformation, which kind of reorders and mixes up our dimensions. And now we can do the standard coupling transformation of splitting things, running things through the coupling network, passing them through the coupling transformation, and then concatenating the result together to get the final output. Okay. So those are coupling flows. But what exactly is that coupling transformation? I still haven't told you what F hat is. And that's because there's lots of different options for it, all right? Some of the earliest works in normalizing flows simply used an additive transformation. This is very limited in certain ways and is not particularly widely used, although it does have the added advantage that the determinant is always 1. The determinant of the Jacobian is always 1. There are affine transformations. This is probably the most commonly used normalizing flow or coupling transformation in the literature right now. This was originally used in real NVP, but has since been used in GLOW, and many application papers that you will see, and then some of which we'll talk about, will work off of this kind of basis of affine coupling layers. And there's many other variations that have been introduced in the last 2 or 3 years. So you can use certain forms of multi-layer perceptrons applied element-wise. You can use a mixture of log CDFs, logistic CDFs, which was introduced in the Flow++ paper. You can use splines for these transformations, etc. So lots of options for what goes in here. For the most part, some of these other transformations, they have certain advantages. We don't really, but none of them have been, let's say, conclusively shown to dramatically outperform affine flows, particularly for images. They can, however, be quite important for other domains. Okay, so what does that affine transformation mean? Well, if we just go back to this figure that we had before, all it says is we're going to replace this with an affine transformation, and we're going to replace this with a scale and translation, where the element-wise scaling and translation that gets applied are functions of the other half of the parameter space. Okay. Now, one of the problems with coupling layers generally actually comes back to that Jacobian. Okay, so the expressiveness of these flows is actually limited in a sense by how densely this Jacobian can be populated. Okay, and so if you have an affine coupling layer, like we've been talking about, then the Jacobian looks something like this. Okay, so we have this big dense block on the lower left that corresponds to that coupling network potentially, and then we have these diagonal elements on the top. All right. But it turns out that we can actually do something kind of clever with coupling flows, which is that we can apply them recursively. And this is some work that's just on arXiv this year, called Hierarchical Invertible Neural Transport, or HINT. And all HINT does is it says, let's recursively apply coupling transformations. Okay, so when we split XA and XB, what we're going to do is XA is going to go through another coupling transformation before the affine transformation is applied. And similarly, after we compute the parameters of the affine transformation, XA is now going to undergo its own coupling transformation. Note that all of these things still preserve the invertibility of the entire transformation, and each one of these recursive things basically takes one of those two blocks and does a further subdivision. And what that means is that the Jacobian of an entire hint transformation goes from looking something like this in the case of a single coupling transformation to recursively filling in this Jacobian with other blocks like this. Okay, but the overall determinant and invertibility still remain more or less the same and remain computationally tractable. Okay, so these are coupling transformations. Let's talk about a couple of other types of normalizing flow models. Right. The next one we'll touch on briefly relates to a class of generative models that I haven't mentioned before, but which you might be familiar with, autoregressive models. So they are based off of the product rule of probability, which basically says you can take any multivariate distribution, and you can write the joint distribution over all those dimensions, all those variables, as a product of conditional distributions in a fixed sequence, right? In fact, any fixed sequence you want. So you have P of x1, P of x2 given x1, P of x3 given x1 and x2, and so forth and so on, okay? And what I'm going to just show really quickly here is a connection between normalizing flows and autoregressive models. And in fact, you can view autoregressive models as a form of normalizing flow itself, all right? And how are we going to do that? Well, we're going to do that by using two things. So first off, we're going to assume that we have Gaussian marginals for our autoregressive model. Okay, what does that mean? So that means the probability of xi given all the previous xi's is going to be Gaussian, and the mean and variance are going to be some arbitrarily complex nonlinear functions of the previous mean and variance, the previous xi's. Okay, and now we're going to apply the reparameterization trick. Okay, those of you that have studied VAEs will know this quite well, and it's used elsewhere as well. However, you can also just view it as simply using a basic property of Gaussian distributions, that if you take a mean zero unit variance Gaussian, you scale it and you translate it, then you get a Gaussian distribution with some corresponding mean and variance, right? And so we can write xi as mu, as this mean, plus sigma times zi, where zi is just a sample from a zero mean unit variance Gaussian. And now you start to see the connection to normalizing flows, because the distribution over x is simply this transformation of some simpler distribution over z, right? And this is the idea, the core kind of idea behind autoregressive flows. In particular, affine autoregressive flows follow this structure. And we can take that expression that I had before, and I'm going to write it in terms of the inverse, and that's just a matter of convention, okay? Because in normalizing flows, the way we've set up the notation here, the function f maps from the complex distribution to the simple one, and therefore the inverse transformation is the one that maps from a simple Gaussian distribution to a more complex data distribution. But that's fine, because we can just invert it and compute the other direction as well. And the determinant of this is actually going to be quite simple, because it's simply a product of all of those inverse scale factors, right? This will be just a basic derivation. So one of the issues of autoregressive models generally, however, is that sampling is inherently sequential. Okay, that conditional product structure that we get means that if we want to generate an image, we have to do it one pixel at a time and wait until we have all the previous pixels generated before we can generate the next one. Okay, and that makes it very inefficient for sample generation. However, the converse, though, is that density evaluation is actually relatively efficient. Okay, and that's why training autoregressive models is relatively efficient, because that density evaluation, that log likelihood, is efficient, even if the sampling process might be somewhat slow. But this was observed in the normalizing flow literature in the context of using these things. And so this is where something called the inverse autoregressive flow was introduced, which basically says these functions are themselves invertible transformations. And therefore, if we want sampling to be fast, then we can just flip the order. We can just flip which one is going to be the inverse and which one is going to be the forward transformation. And the determinant, we get a 1 over, but the determinant basically is more or less the same. And now we have a flow for which density evaluation is potentially going to be slow. Okay, so transformation from the image into that simple Gaussian space is going to be slow and sequential. However, the generation process is going to be quite fast. And that actually turns out to be a useful construction of a flow in the context of variational autoencoders, which is one of the applications of normalizing flows, using them as the approximate posterior in a VAE. Okay, those are autoregressive models. Next, I want to talk a little bit about scale and computational complexity. And so one of the things that was realized very early on with normalizing flows is that flows have to preserve the dimensionality of the data, right? In other words, if you have a 1 megapixel image, then every single transformation has to preserve those million odd dimensions, all right? But of course, that's incredibly expensive in high dimensions, and in deep learning, we're typically used to this idea of like gradually throwing out information, which both has some benefits in terms of representation, but also has a very significant benefit in terms of computational complexity and potentially number of parameters and model size and things like that, and memory usage and so forth and so on. And so that seems like a major limitation in normalizing flows, and indeed this was realized very early on. This is in the real MVP paper by Lawrence Din and others. And they had this simple idea that says, well, what if we just stop using subsets of dimensions? Okay. Practically speaking, this acts like dropping dimensions. Okay, this acts like we're throwing away dimensionality. Okay, let me walk you through what this looks like, and then I'll tell you why it is that this is actually okay, even though we have to have these invertible transformations. So what we're going to do is we start off with our high dimensional vector x here. Maybe we apply some flow transformation f1 to it. We apply this on the full dimensionality. Okay, but now what we're going to do is we're going to take the top half of this, and we're going to split it off, and we're going to put it off to the right here. And now we're going to take the bottom half and we're going to continue processing the bottom half with, say, F2. And we're going to repeat this. Now F2, at the output of F2, we're going to split that in half, and the top half we're going to stick over here, put it away. And then the bottom half, F3, we're going to maybe process that again with some other flow F3. Okay? And now the entirety of this Z is going to be our output, right? So note that F1, F2, F3 all work on successively lower dimensional representations. Okay, and so therefore the amount of memory, the amount of computation that's done by F2 is less than F1, and F3 similarly is less than F2. Okay, but we haven't actually discarded those extra dimensions. All we've done is we've kind of short-circuited them to the end and stuck them directly into the latent space representation Z. Okay. Mathematically, we can just view these multi-scale flows as just a special form of coupling flow, where the coupling transformation, the coupling network is constant. It doesn't actually depend on XA, okay? And so this is basically, XA just never gets touched and it never even gets used after some point, okay? But of course, as I was saying, it's important that we keep track of these drop dimensions in order to preserve invertibility. Okay. There's one issue that comes up both in multi-scale flows as well as in coupling layers, which is how do we split the dimensions for images? Okay, so far I've only been just showing you these nice little cartoon vectors. We split them in half, we randomly permute them, whatever. What's the most natural way to do it for images? Well, channel-wise, but the problem is we only really have 3 channels, okay? So we really can't do a lot of splitting, both either for coupling layers or for these sorts of multi-scale operations. And so how do we get around this? Well, we basically are going to create some more channels by squeezing and getting rid of spatial dimensions. Okay, so if you think of, here's a nice little 4x4 image, what we're going to do is we're going to take every other pixel in every other row, and we're going to combine them together and put, we're going to take every 4x4 block of, or every 2x2 block of pixels, and we're going to stack them together channel-wise. Okay, so this is going to be the first pixel in our resulting image. This is going to be the second pixel, third pixel, and fourth pixel, right? And now we've gone from a 4x4x1 image to a 2x2x4, right? Or in general, n by n by c to n over 2 by n over 2 by 4c. And now we can basically kind of squeeze and reduce spatial resolution as we process these, as we transform these distributions, which allow us to do these sorts of multi-scale tricks, and as well as these coupling transformations. Okay, but we can now do them all channel-wise. Okay, so far I've talked primarily about discrete time normalizing flows. Okay, and what do I mean by discrete time? I mean, we start off with some complex distribution, and we're going to apply a discrete set of steps of transformations. F1 to get to this next distribution, we're going to apply F2, and then F3, and then F4, and now we put this whole thing together, and now we have our entire transformation, which is going to be this composition of these discrete set of transformations. Okay, this somewhat begs the question of what happens as the number of transformations increase, and maybe I'm going to just expect that the transformation by each one decreases, okay? You can look at the limit, in essence, of an infinite number of transformations, and that gets us to something called continuous time normalizing flows, where you can think of a continuous deformation of the probability distribution instead of these discrete, rigid transformations. Right, and this can be done. This can be done through the use of ordinary differential equations. And many of you have probably seen, or hopefully have seen, the Neural ODEs paper from NeurIPS 2018. Strongly encourage you to check it out if you haven't. It's a very cool paper. And this was put to good effect, put to good use in normalizing flows in a paper called FFJORD. And the idea is very simple. It's just as what I was describing, which is that we're going to use ordinary differential equations and the solutions to initial value problems as a normalizing flow. So in other words, our function f of x is going to be something like this. So it's going to be, let's say, y0 plus the integral of some differential equation starting at time t equals 0 and going to some fixed point in the future times t equals 1. Okay, and what you're going to learn are the parameters of that differential equation h. All right, and so you can think about it like this. Here we have time and we have some latent space z, and we can see how we gradually transform that latent space from a unimodal Gaussian distribution into this multimodal distribution at the end of the procedure. And the inverse is actually quite nice because it's really just the reverse. The inverse is also a differential equation, which is found simply by taking the end condition z in this case and reversing the order of integration of the same differential equation. Okay. The change of variables becomes a bit different in this context, in which case it is this it's the integral of the trace of the Jacobian of that differential equation. This is also the divergence. This is what's known as the divergence of the vector field. This can be the trace of this is unfortunately quadratic in the number of dimensions in terms of computation. So to compute this exactly is quite expensive. However, the FFJORD paper introduced the use of this Hutchinson trace estimator, which basically shows that in expectation, this integral over the trace is equal to this integral over the Jacobian multiplied by a vector, epsilon, which is much more computationally efficient to compute. And so you can apply these models. They work quite nicely. This is just a set of toy distributions that you see here, the target distribution and then the corresponding learned density as training, after training during the simulation, right? So they all start off as this big, Gaussian blob, and then you see that blob distribution gradually stretched and spread out in order to create these different, more complex distributions, whether it's a ring of mixtures of Gaussians or a checkerboard pattern. Okay. These neural ODE-based flows are a very interesting direction of research right now. They can approximate almost any transformation. They work quite well in that regard. However, they do tend to be slow and limited to relatively low dimensional data. I'll note that this is more or less a limitation for now, in my view. There's a lot of very exciting work happening right now looking at ways to regularize or other ways to construct the differential equations in order to ensure that they are not as computationally expensive and potentially extend them in their application to images. To date, they haven't really been particularly successfully applied to images just because of limitations around computation. Okay, almost here, almost at the end here. The last piece that I'm going to talk about is training with maximum likelihood. Now, I've already told you training is relatively straightforward in that we have the ability to compute the log likelihood and the density of our probabilistic graphical model directly, and as a consequence, we can just train it directly with maximum likelihood, and that's true, all right? But one of the challenges, especially in the context of computer vision, is that normalizing flows are a model of continuous data. And if you really stop and think about it, we don't have continuous data. What we actually have are pixel intensities, which have been discretized or quantized to some number of bits in order to represent them as, an 8-bit sRGB image, for instance. Okay? And it turns out this is going to cause some problems with maximum likelihood training. And this is something that's kind of well known in generative models that are trained on images. And so this is something that we have to take into account and deal with. Otherwise, the model will find singularities and basically not actually learn interesting structure about the distribution instead. Okay. So what we actually really technically want to optimize is this thing here, right? So this capital P here, this is going to be the actual probability, so the probability mass of a discrete set of values, which are the pixel intensities y, all right? And so what we're going to do is we're going to represent, if we want to represent that in terms of a continuous distribution, we're going to represent it this way, because we're going to assume that there is a continuous density underlying our intensity values, okay? But it's just been rounded or truncated to the nearest integer for the purposes of our representation. And so we can actually directly represent that in our learning procedure, where we have this probability density of the underlying continuous values, and then we have some quantization noise. So this is basically the density of quantization, changes in intensity caused by quantization, right? And so you can think of this simply as, you know, a distribution over 0 to 1, because these are the values that will round to, or maybe be floored to the same intensity value, okay? So the simplest choice of all of this is to just take the distribution over U as a uniform distribution, okay? And then what we do is during training, we dequantize the data by simply drawing a sample from this uniform distribution and adding it to all of the pixel intensities that we have. And this basically turns our discrete distribution into a continuous distribution through this process of dequantization, okay? And indeed, uniform dequantization is what is most commonly used in the literature right now. However, you might look at this dequantized distribution and say, well, that's not a particularly realistic looking continuous density, right? And it's probably not what the distribution of the underlying continuous density actually looks like. And so another perspective on this, which was introduced in a paper that came out last year called Flow++, is that we can view this PU as actually as a variational distribution in a bound on the discrete likelihood, okay? But that through doing that, that means that we can actually learn this variational distribution, and we can learn it to be conditional on the intensities themselves, and that allows us to construct much more natural dequantized distributions that are much easier for the normalizing flow to fit. And these are indeed variational dequantization approaches are indeed some of the most performant in terms of computed log likelihoods or bits per dimension, which is one of the kind of common metrics that we use. So to conclude all of this, we can use all these ideas to kind of describe and characterize many commonly used normalizing flow architectures. So I've just written here what are kind of 4 of the either historical or kind of commonly used standard architectures that exist. So with NICE, you have additive coupling layers and a diagonal transformation, which was, you know, some of the very early work. Real NVP introduced affine coupling as well as the channel-wise permutations. GLOW and Real NVP also introduced the multi-scale transformations. GLOW introduced this channel-wise linear transformation. And then Flow++, as I mentioned, introduced the variational dequantization, as well as the mixture of log CDF coupling transformation that I alluded to earlier. So to conclude, I want to thank you for your attention. This has been a very quick introduction to normalizing flows. There's a lot more out there. A couple of references for you to go and look at for more information, including 2 relatively recent review articles that go into and kind of cover the state of the literature much more in depth and much more broadly than this introduction had the opportunity to. I would also note that this is a very fast-moving space, and so there's lots going on and lots of exciting new stuff that's coming out every year. The most recent ICML that I finished just a couple of months ago indeed had a couple of really excellent and exciting papers. And at least on behalf of myself and the tutorial organizers, thank you for your attention, and I hope you stick around and watch some of the other tutorial videos on different applications of normalizing flows, as well as please do feel free to come to our tutorial slots and ask us any questions on any of this material. We'll be happy to do our best to expand on it and answer your questions. Thank you.